Alright, hello everybody. So today we're talking about partial derivatives. And I'll say here, so what we're talking about, so I'll say we are now going to look at functions of two variables. So f of x comma y. So now, usually y was the output of our function, but we're saying that now we have a function of both x and y, and our output would be, say, z. So we've actually got a function that depends on two variables. So earlier, x was the dependent variable, y was the independent variable, but now these are both dependent variables. And spits out a number. So functions of two variables of f of x, y, which takes in a point x, y, and spits out a number z, right? So we're putting in x and y, and we're getting at z. So it turns out that many real-life measurements will depend on multiple variables or parameters. So let's write down an example here. One example is the heat index, which you might have heard of before. So let's call it I. So the heat index I is a measure of how hot the air feels. Okay, right, so temperature is how hot the air actually is, but heat index is how the air actually feels. Due to actual temperature T, so T plus humidity H. So the heat index I equals F of T and H is a two-variable function. Okay, so we've established this is our heat index. It's a function of temperature and humidity. And the question is, what can we say about I, or heat index I, if the temperature stays the same, but the humidity starts to rise? Or what happens if the temperature starts to rise, but the humidity stays the same? So in both cases, we're treating one of the variables as a constant, because we're saying temperature is fixed and humidity is starting to rise. So we're looking at, well, if we fix t to be a constant, then what is the rate of change of the function with regards to h, disregarding t? So that's what we're looking to answer, and I'll say that we'll answer questions like that using partial derivatives. So I'll say here, let me write down partial derivatives. Partial derivatives help us understand the impact of each variable on the function as a whole. so let's write down here a definition. So definition, if f is a function of two variables f of x comma y, then f has two partial derivatives fx of x and y and fy of x and y. Okay, and now we can go ahead and define what these two things are. So fx of x and y is going to be equal to the limit as h goes to 0 of f of x plus h comma y minus f of x comma y over h, and let's define here fy of x and y is going to be equal to the limit as h goes to 0 of f of x comma y plus h minus f of x comma y over h. So you can kind of see what's happening here is this looks a lot like our definition of the derivative, except for when we define the derivative, we only defined it for one variable. So it was f of x plus h minus f of x over h. But what we're doing here is we're saying y we're going to treat like a constant, and we're going to take the derivative with respect to x, that's this, and here we're treating x like a constant and taking the derivative with respect to y, that's this. Okay. So we call this the partial derivative with respect to x, and this one the partial derivative of f with respect to y. And some notation here is going to be if z equals f of x, y, then we write, so here the first thing is that fx of x and y, so the partial derivative with respect to x, we'll write this as, we can also just write fx, that means the same thing. We can also write this notation. Let me actually write it well since it's the first time I'm introducing it. Right. So instead of a d, we write this symbol, which means partial derivative. And we'll also write, we can also write that this is the partial with respect to x of f of xy. We can also write, since f we said was the same thing as z, we can also write the partial of z with respect to x. And this we can also write as, this should be a d, d x f. Right, so all these things mean the same thing. All these things mean the partial derivative of f with respect to x. And if we wanted to do this with respect to y, we would do the exact same thing. Right, so we can write this as fy. We can also write this as the partial of f with respect to y here, which is the same thing as this, which is, of course, the same thing as this, which is, again, the same thing as this. Okay, so that's how we write that, but let's actually do an example of how we can use these partial derivatives. Okay, so example number 1, we'll write here find fx, fy, and fz if f of x, y, z equals e to the xy times the natural log of z. Okay, so now what we see is happening here is actually we have a function of 3 variables. So earlier I said we had a function of 2 variables. Now we've got a function of 3 variables, and it turns out it doesn't matter how many variables we have. We can do it the same way every time. So when we're taking our partial derivatives, this is the partial with respect to x, then y, then z, we're just setting, let's say we're taking the partial derivative with respect to x, we're setting y and z to be equal to constants. So we just treat them like constants for our integral. Or sorry, not integral, derivative. So the first thing it tells us to find is fx. So the partial with respect to x, treating y and z like constants. So natural log of z, I'm going to say in this case, is just some constant. Y is some constant as well. So if we're taking the derivative of a constant times e to the power of some constant times x, then we just, well, the natural log of z, that's a constant, so we can factor that out of the derivative. And now we're taking e to the power of some constant times x, and we're taking the derivative, so we use the chain rule. So the chain rule says that we would have e to whatever we started with times the derivative of xy. But remember, we're taking the derivative with respect to x, treating y like a constant. So if we take the derivative of this treating y like a constant, then this would be x natural log of z times e to the x y. And that would be our answer. Okay, so I encourage you to try to do these for each of these. But let me just work through one more here. So if we had the derivative of this now with respect to y, again, we treat this natural log part as a constant. We treat this x as a constant. So since natural log of z is a constant, we'll just factor that out in front. So natural log of z times, again, we use chain rule to solve this. So it's e to the xy times, so here I just wrote the derivative of xy. This is supposed to be with respect to x. So to make things a little bit more clear, this time I'll actually write the derivative with respect to y of xy. Right, because this was the derivative with respect to x. Oh, sorry, that's, ooh, goodness. What I meant to write here was y. Right, the reason for that is we take the derivative of this with respect to x. X is the variable, so that's the one that goes away. Right, so now we're taking the derivative with respect to y. Y is the variable, x is the constant, so the y needs to go away. So this would be x natural log of z times e to the xy. Okay, and now our last step is we need to take the derivative with respect to z of our original function, right? So this e to the xy, that's just a constant because x and y we're treating like constants. So we just say this is e to the xy out in front because we can always just factor a constant out of the integral. And now we take the derivative of natural log of z with respect to z. So that would be 1 over z. So our answer here is e to the xy over z. Okay, so we found all 3 of the things that we needed. Okay, so that's that example. Sorry, I made a little mistake there. So now we can look at higher derivatives. Okay, so we can take partial derivatives of partial derivatives with the notation. Okay, so remember whenever we're just doing normal derivatives, we can take a second derivative, a third derivative, and so on. So we can take derivatives of derivatives. We can do the same thing with partial derivatives. So let's say we start with the derivative of f with respect to x, the partial derivative of f with respect to x. Let's say we would, again, after that, so whatever our function was there, we then take the partial derivative of that with respect to x. So if you do that, that's the same thing as fx, so the partial with respect to x. And you take the partial again. So this is now our notation that we would write for this is this. Right? So this is the notation we would use if we take two partial derivatives with respect to x. Let's say we instead did partial derivative with respect to x, and then after that we took the partial derivative with respect to y. So you always read these from left to right. So you do the left thing first, then the next leftmost, and so on, right? So the leftmost one, and then the one next to that, and the one next to that, and so on. So that's the order we read it. So first we do the partial with respect to x, then we do the partial with respect to y. So you can write this as the partial with respect to x, and then taking the partial derivative of that with respect to y. And you can write that as this. Okay. So that's two of our options. So this is a function of x and y, let's say. Well, we've also got two more options. So the two options that I haven't written down, at least one of them, is f, y, x. So that's first taking the partial with respect to y, and then taking the partial derivative with respect to x. So if you wanted to write that, you would write that like this. And our last option is, let's say we take the partial derivative with respect to y, and then we again take the partial derivative with respect to y. So that's f, y, y, which is, we can write like this. Oh shoot, I messed this up a little bit. Okay. So that's how we'd write that. But let's actually do an example of how to take second partial derivatives. So let's say we have example number 2, and it says find all second partial derivatives of f of x, y equals x cubed plus x squared y cubed minus 2y squared. Okay. So it says find all second partial derivatives. So let's just list out what our options are. So we need to find, so let's say we need to find, let's say we first take the partial with respect to x. Well, one option is then we take the partial with respect to x. Another option is first take the partial with respect to x, then with respect to y. Another option is first take the partial derivative with respect to y, then x. And our last option is partial with respect to y, and then y again. Right, so we've got to calculate all of these things. So let's first take the partial derivative of f with respect to x. So again, remember, we're treating y like a constant here. So if this is a constant, then this goes away, right? This term is going to go away. This term is a constant times x squared, and this term is x cubed. So now we just take our derivative with respect to x. The derivative of x cubed is 3x squared. The derivative of a constant times x squared would be plus that constant times 2x. And then remember, this is a constant, so this goes away. And let's alternatively look at if we took the partial derivative of f with respect to y, right? So now we're treating x like a constant. So this term is like a constant. This term is a constant times y to some power. So we're going to rewrite the constant and then write the derivative of the y term. And then minus, now we take the derivative of this with respect to y. So that would be 4y. Okay. Now, well, we found our first derivatives. So we found the derivative with respect to x, and we found the derivative with respect to y. But next, we want to find, so we start with this function, and then we take the derivative of that function with respect to x. So if we do that, then notice the first term, if you take the derivative with respect to x, becomes 6x. And the second term, we're saying y is like a constant and x is the variable. So if you got some constant here times x, then whenever you take the derivative, you're going to get 2y cubed. Okay, and now let's go ahead and say, well, our other option here was to take what we started with and then take the partial derivative with respect to y. So if we did that, then doing this, notice if we're taking the partial derivative with respect to y, well, I'd encourage you to think about what that should be. But here, we're taking the partial derivative with respect to y. This is a constant, so that goes away. This is a constant. So we've got the derivative of this, which is 3y squared times the constant that's left over. Right. So that would be our answer for that one, which we can rewrite as 6xy squared. Okay. And now we've just got two more things that we need to find, right? So one option was we start with our partial derivative with respect to y, and then we take the derivative of that with respect to x. So remember, this thing is a constant because we're treating y like a constant if we're taking the derivative with respect to x. This is a constant, this goes away. And now we've got some constant, 3y squared, times the derivative of x squared, which is 2x. So again, we're going to get 6xy squared. So we actually get the same thing as if we did in the other order. Notice that's not always true, so it does actually matter the order in which you do these things. So if you take the derivative with respect to x and then with respect to y, it turns out in this case, it's the same thing as if you took the derivative with respect to y and then took the derivative with respect to x. That's not always the case, so you need to be very careful the order in which you do these things. You always read them from left to right. So this notation means that first we did the derivative with respect to x, and then we did the derivative, well, in this case it's the same, with respect to x, but this here says first we did it with respect to x, then with respect to y. Okay, and we've got one last thing that we need to figure out here. So we started with the partial with respect to y, and what if we then take the partial of that with respect to y? So again, we're treating x like a constant and y like a variable. So this part here is a constant. 3x squared is our constant in front of y squared, and we need to take the derivative of y squared. So times 2y minus, now we take the derivative of this with respect to y, that would give us negative 4. So this is actually 6x squared y minus 4. So these are our answers. This is the partial with respect to y and then y again. This is y then x. This is x then y. And this is x then x again. Okay.